Hello, my name is Julia James, and this is my Physics 2212 Faraday's Law lab. Starting off, I would like to outline the purpose of this lab and some important physics principles that help to explain the theory behind the lab results and calculations. The purpose of this lab was to collect observational data of a magnet falling through a conductive tube of aluminum foil and to model it computationally to describe Faraday's law and relate time-varying magnetic field to a Curly electric field. For this lab, my method was to first complete a real-world experiment with a magnet and roll of foil, and to then create a computational model to simulate the experiment. The results of this lab showed that the average falling time for the in-person experiment was 1.19 seconds, while the computational model's predicted falling time was 1.12 seconds. The first important physics principle to note is the Biot-Savart law, which explains the magnetic field is generated by moving electric charge. It is used to calculate magnetic field created by currents in a conductor. The equation for this law can be seen below. The next relevant concept is the field of a bar magnet or dipole. Because of its structure, a bar magnet can be treated as a dipole, and it is a closed circulation of an electric current system. The general formula for the magnetic field of a dipole is shown below. Another important physics principle to note in the main law for this lab is Faraday's law. Faraday's law relates time-varying magnetic field to a Curly electric field. It says that a changing magnetic field induces a voltage that can drive electric current. The formula for Faraday's law can be seen below. It says that EMF is equivalent to the change in flux over the change in time. Finally, there is Lenz's law, which states that the direction of an induced current always opposes the change in the magnetic field that caused it. This is because nature likes balance, and it does not like a change in flux. Lenz's law is responsible for the minus sign seen in the equation for Faraday's law below. For this lab, the system is the falling magnet, aluminum foil tube, and earth. There are no surroundings. For this lab, we operate under the assumption that the only forces acting on the magnet are gravitational force and force from the aluminum foil loop. The drawn model represents all relevant forces, including gravitational force, which acts in the downwards direction on the magnet, the force on the magnet due to the loop of foil, and the magnetic force on the loop due to the magnet. To perform this lab, we first had to mark the north pole of the magnet. We then took relevant measurements including the mass of the magnet, width of the foil, inner radius of the tube, and length of the tube. We then dropped the magnet through the foiled tube 5 times, recording how long it took for the magnet to enter and exit the tube each time. The video to the right shows one of these trials for this process. Finally, after completing 5 trials, I used GlowScript to computationally model this process so that I could compare observational results with computational ones. Here you can see the results of the in-person component of the lab, along with all recorded values. After completing all 5 trials, we found that the average time it took for the magnet to enter and exit the tube was around 1.19 seconds. Note that while this seems like a short period of time, it is longer than it would have been if there was no magnetic field present. This slide represents the first portion of my code that identifies the constants and initial conditions measured during the experiment. I input the length and width of the foil, inner radius of the tube, mass of the magnet, and mu value from Lab 3. This portion of my code outlines where I laid out the needed formulas to calculate magnetic field of the dipole and the flux equation. Finally, this portion of my code represents the simulation loop to run the computational model. This code accounts for all assumed forces and outputs a graph showing the magnet's velocity over time. Here is the resulting computational model. As you can see, the calculated time for which the magnet was in the tube is 1.12 seconds. This is 0.07 seconds faster than the time that was found during the in-person lab experiment. Some potential sources of error that could have led to this discrepancy are that there could have been inaccurate timing during the lab experiment. Another source of error could be that there was some contact force between the magnet and the walls of the foil tube. Finally, another source of error could be that there was air resistance or other outside forces that were not accounted for in the computational model. To answer the follow-up question, if the resistivity of the conductor were reduced as close as possible to 0, there would be a larger induced current because resistance would be nearly 0 and current is inversely proportional to resistance. This larger current would mean there is a larger magnetic field and more magnetic force in the loop, meaning the force on the magnet by the loop is also greater per Newton's third law. Hence, the magnet would fall with less speed and take longer to exit the tube. To answer the second follow-up question, if holes or slots were cut into the tube, the holes would disrupt the continuation of the ring structure of the tube, reducing the induced current and causing there to be less magnetic force on the loop and on the magnet. Hence, if holes or slots were cut into the tube, the magnet would fall with greater speed and take a shorter amount of time to fall through the tube. This concludes my Physics 2212 Faraday's Law Lab. Thank you.